So we've been talking about derivatives. So somebody give me a synonym for derivative. Slope or rate. Those are two good ones. So we're going to do some stuff with graphs today that are going to involve slopes, and we're also going to connect calculus to physics for a day and talk about some rates. So anybody who's in physics, can you give me a definition or word we've ever seen that had rate in it somewhere that you've said on tests, something about rates?
Acceleration.
Acceleration. What is acceleration? A rate.
Change of velocity.
It is. So acceleration, we're going to have some acceleration problems today because acceleration is the rate of change of velocity. How I could use calculus symbols instead of lots of English words to do that. I could tell you that acceleration is the derivative of velocity. Another rate from physics. Velocity is another rate. Velocity is the rate of change of displacement, where S just stands for displacement. So as we do the homework tonight, anything with an S is displacement. If they ask you to do anything with velocity, just do the derivative of displacement. If they want the acceleration, you could do the derivative of velocity. Or, if you had to start from displacement, how could you get to acceleration? Second derivative. If we do the second derivative of displacement, that's also acceleration. Acceleration is the first derivative of velocity, which was the first derivative of displacement. So acceleration is the second derivative of displacement. Distance versus displacement. What's the difference in distance versus displacement? Time back into physics again.
Displacement includes direction.
It does, and distance doesn't. Distance is a thing called S word. Scalar. Displacement is a different word. Vector. Distance is displacement similar. Displacements just don't have direction. So displacement, sometimes distance is just the absolute value of displacement. Like, one way I could describe direction to you would be if this is a displacement of 1. We had that down, so I'll go instant replay. If this is a displacement of 1, what would this be a displacement of? Negative 1. But that would be a distance of 1, while this is a distance of also 1. Okay, distances are always positive, non-directional. Displacements might have a direction associated, whether that's north, south, east, west, or whether that's positive, negative. Speed and velocity, likewise. Speed is sometimes simply the absolute value of velocity. Velocity might be positive or negative depending on directions. Like if I throw this up in the air with a velocity of 10, it comes back to my hand with a velocity of
1.8.
Nope. So I go, initial velocity is 10. The velocity right there when I caught it would be
10 is 1.
Speed would be about 10. But if
negative 10.
Negative 10, because velocities have direction. So velocity might go positive, negative, depending on direction. Speeds just have to be positive. Maximum height. We did some physics problems where we were like firing things in the air. It hits the top just like my chalk did a second ago. What do you know at the top when things hit the top? It's not the 9.8 thing. You mentioned 9.8 a second ago. 9.8 is not going to be used by the calculus book at all, I don't think. 9.8 is the acceleration of airborne stuff, but in metric world, in meters per second squared. Our book does some stuff with 32. That's more the American-based feet per second squared, but you don't have to memorize those numbers. But something else is going on at maximum height. What does my chalk do there?
Stop.
It stopped. In terms of S's, V's, and A's, what do we know about one of those items when something stops?
Acceleration is 0.
No, the acceleration was always 9.8 in
Oh, it's the
metric.
velocity.
It's the velocity. The velocity is 0 when we hit maximum height of an airborne object. Also worth a mention, any question in the homework that mentions average anything, including average velocity, that's going to be just an algebra question. There are some homework questions here tonight that it's just algebra based. But anything that asks you for an instantaneous rate of change, that is going to be a calculus problem. That's going to be derivatives. And a little bit we've talked about that in physics, just, real physics is calculus based. It just is. Our physics book takes it a little bit easy on us sometimes. It just sticks to some algebra-based problems, but that's maybe not reality for us. Question about that? So let's jump in. I'm going to do one homework problem first, just straight out of the block. If you want to join me, I'm on page 147 is where the new homework is. 147, there's a 1 to 8, that all 8 of these questions are about the same in structure. But this is what they'll give you. They say, we're going to give you a position equation, a displacement equation, S equals, in this case, it's 0.8 t squared. They're saying, we're going to give you a timeline here, the starting time of 0, finish time of 10. And then they're going to ask you some algebra questions, and they're going to ask you some calculus questions. So first in part A, they say, find the displacement and the average velocity for this time frame. So if they're saying average velocity, is it time for calculus?
No.
No. So what they're asking us to do is figure out where are you at the end. In other words, plug in the 10 seconds. If we plug in the 10 seconds at the end, what number would you get?
50. Oh, that. 4.
Eighty. 80. So 10 squared, 100 times the 0.8 is 80. Also figure out where you are at the beginning, which for this story we're plugging in. The 10s you plug in for the end, plug in for the beginning of the story must be 0. Plug in 0, you catch a break because you get out 0. You won't always get out 0 on that other one. So if they want you to figure out how far we went, this is telling us at the end of the story we were at the 80-meter mark. At the beginning of the story you were at the 0-meter mark. So how far did you travel? 80. Because you did like 80 minus 0 is 80. But in a different question it might be 80 minus something is something. But you're going to have to, for part A, plug in, figure out where you are at the end, plug in, figure out where you are at the beginning. They're giving you the numbers to plug in, get 2 results. Subtract, always end minus beginning, to subtract in that order to figure out what you do. That's half A. So they said find the displacement. We did. Then they want us to find the average velocity. Average velocity is distance divided by time. How much time did this story last? 10 seconds. From 0 to 10 is 10 seconds. So we take the 80 we just got, divide by 10, and that's 8. What if this went from 1 to 10? Then we would have just divided by 9. I'll stick a note on here. That was the 10 minus the 0 is how we fed into that. In another question, you might actually have a subtracted it. It's not just stealing this 10, it's the difference between beginning and end. A for algebra. Question about the A's. In B, they say find the speed and the acceleration at the beginning and at the end. They didn't use the word instantaneous, but that is what they're saying. Is instantaneous speed, instantaneous acceleration at the beginning at that instant, but also at the end, at that instant. So we need to do some calculus. The only calculus you know about is derivatives and limits. So we're not doing limits. We're going to do the derivative to make ourselves new equations. A lot of this homework, they're going to give you a displacement equation, and they're going to expect you to come up with a velocity equation by doing the derivative, which would be
1.6.
c. And they'll want you to make an acceleration equation by doing the derivative again, which would be 1.6. And then they're going to expect you to plug in these numbers to find the instantaneous results. The velocity at 0, if you plug in 0, you'll get out 0. The velocity at 10, if you plug in 10, would be 16. The acceleration at 0, it is just 1.6. And the acceleration at 10 is 1.6. It's sort of weird to plug in because there's variable to height, but the acceleration is just 1.6. So we're not on the Earth. Maybe we're on the moon or we're somewhere else. I don't know where we are. Well, no, that wasn't airborne. That was just going for a walk. The acceleration could have been anything. Question about what you're trying to do with the 1 to 8.
Wait, how'd you get the bottom part of that? Like just that?
We're trying to plug numbers into this, but there's not even a variable, so we just got stuck on 1.6. For this equation, when we plug these numbers in, stuff happened because the variable was still alive at that level. Okay, question 1 to 8 style stuff. Then taking a lead from the homework page, but just doing an example of the book that's like some of the homework. I'm back to 140 if you want to follow along with me. 140, it says there's a dynamite blast and it blows a heavy rock straight up in the air. It has a speed of 160 initially, and here's an equation for the height where it's going to be at different times. S equals 160t minus 16t squared. They ask some questions like how high did it go and what's it doing. But before we can do anything, we're going to need to make more equations. Do the derivatives. Okay. If we do the derivative of displacement, we have velocity. Do the derivative numbers, we get
160 minus 360.
degree. Then if I do the derivative again, if I need it,
Minus
then that would be the
acceleration.
acceleration will be
Minus 30.
negative 32. So what that means is we're on Earth and they're using the English system, not the metric system. Like 32 is the equivalent of 9.8, just if we left metric, we're in America. So then what they're going to do is supply us with some more information in the question where maybe they're going to tell us a distance and we can do some algebra to solve for times. Or maybe they'll give us a velocity and we can solve for times. I doubt that they're going to do much with the acceleration because that's just like that doesn't seem to be going anywhere. But for part A, they want to know how high the rock goes. How high the rock goes, we're back to my idea from 5 minutes ago about maximum height. What did we decide to do about the maximum height?
Velocity 0.
Velocity is 0. So I'm going to go to the velocity equation and put a 0 in where velocity lives. And then let algebra take course. If you solve that for time, what time is going to show up? There's truth there, but then the question becomes, what is the actual question they asked you? Okay? So if they asked you, how long does it take to get to the top, it's 5 seconds. If they wanted to ask you how long it'll take to get back down, still 5 seconds. What if they asked for the total time that the thing spent in the air? Now that's 10 seconds. But I don't think they asked any of that. I think they asked, where is it? like how high is the highest? It involves a time of 5. Let me take a peek at what they asked. Yeah, they want to know how high this rock goes. It's going to take 5 seconds to get there, but where can we answer the question, where is it?
Which 160?
Back to one of these 3 equations can do where it is,
Oh, the top one.
the top one. This is telling us where we are, that's the displacement. So if we want to answer this question, we need to take the 5 and put it up there. The distance, where it'll be, is 160 times 5 minus 16 times 5 squared. Mathy math that up, and I'm saying that's going to be a 400. Something about that. They could ask other weird questions off of that. If it's 400 feet up, then it's also going to be 400 feet back down, which means the total distance the rock covered in its journey was 800 feet. They could ask us stuff like that. Then we'll move up to B. Talk about A. B does a change up. B says, all right, so the rock is on its journey. It's at a 256-foot height. So it's a little more than halfway up. They want to know how fast is the rock going when it's at that 256 line. So, what's the 256 real world height? Which equation does that have to do with? Top one. So we'd go 256 equals this other stuff. And now you're in an algebra world again. How in algebra world would you solve this?
You bring the 256 to the right.
You would, you'd get the thing equals 0, and then you have 2 choices.
Solve quadratic.
You could either do a quadratic formula, which we have a program that we can hook you up with. If you don't have a program that does that, you can do your world. Or what else can we do? Something.
Factor.
It might be a 1 factor. So that's kind of up to you. If you like to factor and stay in tune with factoring stuff, you could. This one seems easier to just use the quadratic formula to do it. But we're going to get, if we do the factoring or you do the quadratic, doesn't matter to me. This is going to show you up a time of 2, but also a time of 8. Why did we get 2 times of when that's going to be at the 256 line? We shoot the thing in the air. How's it going to be at that height twice?
When it goes up, it goes past it.
Once on the way up,
And then it comes down.
and then once on the way back down. So if they asked us when we're at 256, we answered it, 2 and 8 seconds. But I don't think they asked that, and they didn't. They asked how fast is the rock going when we get to this point in time. So which equation answers how fast?
Velocity.
Velocity. So we're going to need to put the 2 into the velocity equation. So if we put 2 into the velocity equation, we're going to come up with 96. If we put the 8 into the velocity equation, we're going to come up with a negative 96. Why didn't they both come up the same?
That one's on the way up. And
Up versus down. So the sign's different because it was headed 2 different ways. If they ask us for velocity, I'd go with those answers. If they ask me for speed, I'd change this one. If they use the word speed, speed has to be positive, so I'd go positive 96. They just said how fast, so I'd probably go 96 and negative 96. If they don't technically use the word speed, I'm not going to get real technical back with them. I'm just going to go with what they gave me. Something about that. And here's an easier question. I'm going to go to 143, and I'm going to read a little bit of example 11 because there's not really math there, and that'll just feed us into example 12. There's a thing in economics called marginal cost. So I'll just read this and see. Bottom of 143, it says, suppose it costs a company some formula, C of X dollars, to produce some steel in a week. It's going to cost more to produce more. And the cost difference, if we divide, would be an average. I don't care about that yet. They do some sort of limit here. And then I think the last paragraph is what matters. Not the figure 329, but it says, we can see if the company that produces X increases its production by 1. The additional cost is going to be given by that limit, which was the derivative. And that's called a marginal cost. The marginal cost is an estimate of how much it costs to produce one more thing. So if I had a factory that produced chairs, and I'm right now producing 1,000 chairs, the marginal cost is how much more will I have to pay if I decide to make 1,001 chairs. If I'm making 1,000 chairs, it probably doesn't cost me much to make chair number 1,001. Like, we make one more chair. It's a big deal. I got the factory, I got the workers, all I have to probably do is show up and say, make one more chair. It's not a big fuss. But if you're a business person, that matters. If we're going to increase the production, how much cost am I going to increase? The derivative gives you a pretty good guesstimate of what that number is. So there's two ways you could do this, and the homework will go both ways. So if I told you I was making 1,000 chairs, and I want to up production to 1,001 chairs, how would you figure out how much extra that's costing me to make that switch? Process in mind at all. This is the formula that tells me how much it costs to do any amount of chairs. If I'm making 1,000 now and I want to upgrade to 1,001,
Would you find 1,000 first, plug 1,000 in,
I can plug 1,000 in to figure out what I'm paying now.
and then you do 1,001.
Plug 1,001 in to figure out what it would become, and then I can subtract. And that would be an on-the-money answer. I could do things that way. They like to do this by doing an estimate. To do an estimate way, you can just do the derivative, which would be
3x squared minus 12x plus 15.
then take the lower original number and always plug in the original number and just see what it does. I'm not going to plug in 1,000 because that's not what the example is going to make me do in example 12. Example 12 saying, here's the cost thing. We're presently producing 10 stoves a day. How much will it cost to produce stove number 11, basically? So if I plug 10 into this, I get a 195. I think there are some homework questions though, that what they have in mind is for you to plug in the 10, you plug in the 11, you actually do the subtraction, and it's probably pretty close to 195. There are others that they just want you to do the derivative and plug in the one number, which is pro for simpler, but con because maybe that's not as most accurate as the things would be. So what about that? There's also a thing called marginal revenue. It's the exact same thing. It's just the flip side of the coin. If you're a business person, you're spending money to make stuff, but you're only doing that to bring money in. Marginal cost is what you're paying out. Marginal revenue is what you get back because of that. So they ask you, they say, same company, same scenario, find the marginal revenue. Well, do the derivative.
3x squared minus 6x plus 12.
And then they want you to plug in the 10. So 300 minus 60 is 240, plus that is 252. So you're a businessman and somebody's crunching these numbers for you, tells you it's going to cost you another 195, you'll make another 252. You're going to say,
So this is
sounds
just
good to me, I'm making money.
just a quicker way rather doing it the whole.
It's a quicker way rather than doing the whole thing out. Because here's another benefit. If then the boss is like, hey, what if we got up to 20 desks? Is that still a good idea? Well, you've already got the formula, plug in the 20s. Okay. Instead of having to plug in 20, plug in 21. You know, do that. Does your life change forever? Not really, but it's just a sneaky way to get a guesstimate of about how much more money am I going to have go out, about how much is coming in, is this a good or bad idea? I don't remember from my economics class what it was called, but there's a point where marginal cost matches marginal revenue, and that's like a big fuss, like they're equal. That's called something, and I forget what it's called because I haven't done economics since like the 90s. It's been a long time since I can tell you my econ class was at 8 a.m. and I can tell you it was tough to stay awake. My main takeaways of econ was watching people go like this every day. I saw one kid hit his head off his desk, like hard. He like banged it. So it was a good time. Question on that? Okay, let's look to the graph paper that's in your hands. So, graph paper that's in your hands. I graphed you a velocity graph. And I'm looking for you to return me a speed graph. We did this in physics, just a matter of recall. How can you turn out a speed graph if I kick you a velocity graph?
Make everything positive.
Make everything positive. So anything that's where has to get tweaked.
On the bottom of the x-axis.
Anything under the x-axis, how are you going to tweak it?
And then make it on the other side.
Yeah, just kind of mirror it to the other side. So through the middle where I have a valley on that graph, if you mirror it, you're going to get almost like a space shuttle airplane looking thing. And then where else needs mirrored that's easy to miss on first glance? Other than that space shuttle through the middle.
Edge, the last part.
Yeah, the very last part, from 10 to 11. So what we're hoping to turn out is something that looks like that. That idea. Good. You zoom in at that top graph, or is that hard to do? Yeah. That's their fault for watching a video instead of being in function. Then we could look at either of those graphs to answer these questions, depending on the question. Moving forward, does anybody have a thought on somewhere that we moved forward? Let's try this. How would velocity be able to tell us whether we were moving forward or moving backward?
When it's positive or moving forward.
Whether it's positive or moving forward. So when I ask you, when is the object moving forward, equivalently I'm asking, when is velocity positive?
From 1 to 3 seconds. Or from 0 to 3 seconds.
0 to 3 seconds is one area. Yup. Any others?
8 to 10.
8 to 10. So moving forward is everything above the axis on the original graph, which is 0 to 3, 8 to 10. Somebody else then take a stab on when's it moving backward. 3 to 7, 10 to 11. I agree. Anybody have a shot then at when we're standing still? I would agree with 7 to 8. I have a bigger list than that. But I like that. From 7 to 8, you're standing still for a full second. But where else are you standing still?
Oh, 1 and 2.
No.
Oh wait, no. At 0?
At 0 for an instant. At an instant, at 0, you were standing still. Where else are you standing still for an instant? At 3. At 3 is where we had been moving forward, and after that we're moving backward. So for just an instant, we must have been standing still while we were like making up our mind what we were doing. Where else do we instantaneously stand still? At 10. I'd agree. You're viewing the x-axis as rest. Anything above the x-axis is moving forward. Anything below the x-axis is moving backward. Anything on the x-axis, it's at rest, whether that's for a second of an instant or whether that's like over a time period. Then we're going to need to shift gears. Speeding up versus slowing down versus constant speed. How would you judge speed up versus slow down versus constant speed? Or do you see a zone where you're confident that you know which category that goes in? Anybody have a thought on speed up versus slow down versus constant speed?
Well, speeding up from 0 to 1.
It is.
Speeding up from 5. Wait, no, sorry, 6 to 5.
It is not.
Oh, 8 to 9.
It is.
There's more.
They are. It is.
3 to 4.
It is.
And 10 to 11.
It is. All 5 of those. So speed up is 0 to 1. 3 to 4, which looks different but isn't, depending on where you're looking. 5 to 6, which is the same as 3 to 4 was. 8 to 9, which is a lot like 0 to 1 was. 10 to 11, which is like how 3 to 4 and 5 to 6 were. All 5 of those are in the same family. Can anybody use words to explain something that we're looking for that can spot all 5 families? Well, I'll help you out. If you're looking at the original graph, the original velocity graph, you'd be looking for anywhere it's moving away from rest. If you're moving away from rest, you're speeding up. And where did we define rest to mean? X-axis. Anything moving away from the x-axis is speeding up. So if you're looking at the original graph, all 5 of those zones we said are moving away from the x-axis. Simpler way to do it, since it used the word speed. Don't look at the velocity graph. Look at the speed graph that we improved. And just look for where it goes up. Speed up, look for speed up. So if we look at the speed graph going up, we find all those same areas. Slow down would be the opposites. Slow down would be anywhere that the speed graph we tweaked is going down, or it would be anywhere that you're moving toward rest. If you're moving toward rest, you are slowing down. So where do we slow down? 2
2 to 3.
to 3 is true.
6 to 7.
6 to 7 is true.
And
9 to 10 is true. And if we didn't do any of those, we must be moving at constant speed because we're running out of choices. You either speed up, or you slow down, or you stay the same. There is no fourth choice to this life. So constant speed, you're not moving to rest, you're not moving away from rest. You're basically just a horizontal life. So that's going from,
1 to 2.
agreed,
4 to 5.
true,
And 7 to 8.
all true. Something about that trio question. So now where did we change directions? Those are all going to be like instantaneous choices. Where did direction change happen?
What's the slope became negative?
Yeah, so like what times?
2 to 3.
No, it's going to have to be just a single time. 3. Before 3, we were positive, meaning forward. After 3, we're negative, meaning backward. So at 3, that was a moment of pause, decide, and change direction at 3. Where else did we get a directional change? At 10, I agree. Previous to 10, we were moving forward. We were slowing down, but we were still moving forward. After 10, we're moving backward. We're speeding up, but we're moving backward. But 10 is a place where direction got changed.
8.
I would say 8. 8, I think, is the decisive moment where you chose to change direction. Coming into 7, you were slowing down, moving backward. And then you took all the rest. 7 to 8, you decided to sit on a bench. But then at 8, you decide to move forward again. I would consider 8 to be the moment where you decided to change direction. Because you had been backward, and at 8, you actually took the initiative to move forward. If I want you to graph acceleration, how can we do that? How does acceleration relate to velocity?
It's a derivative.
It's the derivative. What's a synonym word for derivative?
Slope.
Slope. So let's compute some slopes. From 0 to 1. What's the slope?
30.
30. Because you went up 30 spaces and went over one space, so that's the old rise over run, or delta y over delta x, or whatever you like to do. If you're up 30 in a square, that's a slope of 30. So what you want to do is just one little line up here, horizontal 30, just for 1 second worth of space. 1 to 2 is an easy slope to compute, not by computing, but just from your own memory. When something goes horizontal, it has a slope of 0. So from 1 to 2, for 1 square's worth of space, just draw on top of the x-axis a slope of 0. 2 to 3, what's the slope? Negative 30 for a second. So line up a little step down there at negative 30, from 2 to 3. 3 to 4. I'm going to say negative 10, because we're going off the original graph. Anything downhill is going to be a negative slope. 4 to 5. 0. 5 to 6. Negative 20. 6 to 7. Big comeback. Positive 30. 7 to 8. 0. 8 to 9. 10. 9, 10, 11, that's one smooth, continuous piece of graph there, so we're going to get a 2-second long sequence. It's the same. We can either do 1 at a time or 2 at once, but it's going to be the same answer for us. It is going to be negative 10. So that's going to be just a longer step, I think.
You connect all of them, right? Like,
You don't go vertical lines that connect, though. They be a series of isolated steps, just like that. Feel that? That may or may not help people. That may or may not be easy to zoom in on, but a bunch of steps for acceleration. If people are watching a video, I could send them a PDF or something if they want. Anything uncertainties? We're 2 days of homework on 147, so today's Thursday, tomorrow's Friday. So some would be due-ish tomorrow, some would be due Monday-ish, doesn't matter to me how you parse this up. The syllabus has the numbers on it. You could do it the order the syllabus says, or you could split it up however you want to split it up. We would want to just get that done by Tuesday. We'll do 3-4 on Tuesday. All I got, it's word problems, so some of them are usually, I'd say this is a harder than average homework. Anything that involves a word problem is usually an extra level of just complication to life. That's it.